Okay, then let's continue. So now that we've sketched what we want to do for the rest of the term, it's actually time to start doing it. Again, recall that we want to talk about different examples for designs which are encoded in the design matrix and the beta parameter. And as an example, we use this DLPFC volume dataset that I briefly introduced before. And we will start with what one can call continuous designs. And there we want to now briefly again rehearse simple and multiple linear regression before actually getting to the bigger part of this last bit, which is categorical design. So let's start again with simple linear regression, and this is because we've seen that so many times now. This we can do really quick. So again, to get also you get familiar with these three different ways of writing this. For the individual data points which are modeled by random variables, of course, simple linear regression says that each data point is the realization of a random variable yi, which has as expectation the corresponding value of simple linear regression based on the independent variable. So there is some offset, and there is some slope that is multiplied with the value of the independent variable. Bless you. And of course, it's the realization of a Gaussian random variable, and all of again, all of the experimental units have the same variance parameter as previously also discussed. So that's again the probabilistic way to write things, then the structural way to write things, and this is, I guess, how you always seen this in undergrad statistics, is as this equation. Where in undergrad statistics, I think what is often gets lost is this epsilon I, which, as you know by now also know, is important if one wants. So these parametric assumptions about epsilon I, they are important if you want to use the inference framework of GLMs. So if you want to compute t values and compare them to the t distribution, then of course you need to assume that the errors are Gaussian distributed. If you don't want to do this, and of course you also don't need to assume that the errors are normally distributed. So that's the structural way. Again, it says the same thing. It's just two ways of writing that. And then the way that you are now familiar with writing things, and the thing that we focus on in the entire course is, of course, that the data set itself, so our 32 data points, are the realization from a multivariate Gaussian with expectation parameter x beta and covariance matrix sigma square in. And the question then, of course, is always what is the design matrix and what are the interpretation of the beta parameters. And of course, this is now just an implementation of what we have up there. So of course, and I'm not asking you now, the design matrix can take a column of ones and a column of the values of the independent variable, as we have seen many times. So that's actually an n times 2 matrix, and the beta parameter vector hence is a two-dimensional entity. Sigma square, like always, is a positive scalar, and now the beta parameter vector, of course, encodes the offset which is the A, and the slope, which is the B. Yeah, so there's really nothing new here. So this is what we've seen many times. What kind of maybe is new is that we now apply this to the data that we've seen in our table. So maybe let's scroll up there quickly. So we have this, we have this data set with indexing participants, their age, alcohol, and DLPFC volume. Now, one way one can apply a simple linear regression to this kind of data set is to forget about the alcohol and just view the age as the independent variable and the DLPFC volume as the dependent variable, and then one gets the thing that you're also very familiar with as visualization. You get, for example, here age, and here you get DLPFC volume. If one applies this to this data set, what one actually finds is just how the data was realized, that you have a negative covariation, so this volume goes down, and this then can be the fit. So we've seen all of this many times, so I'm not going into detail again about the difference between the expectation and the beta parameter estimates and the different meanings of these curves. Why I'm doing this visualization is because I will also do visualizations for the other designs that we are doing, because you should, when thinking about these analysis, you should always think about what they mean, what the underlying mathematics is, but also how they are visualized in the literature, so that you, when you see specific graphs that are always the same kind of forms, that you also associate these kind of graphs with the designs that we are talking about. And already in the next example, we will actually see that sometimes people don't use any visualizations. Okay, so that's simple linear regression. Are there questions about this? Because this we've seen really many times. Good. So that's an example for continuous design, because we have this continuous regressor here as the second column of the design matrix. Now let's go to an extension of that, which is multiple linear regression. And multiple linear regression, of course, is if you see this as a kind of own subspace of the large design space that we are talking about, then multiple linear regression is, of course, kind of an infinite space, because you can have many regressors. So instead of only having one column of a continuous regressor, you can, of course, have essentially as many as you want, although that's not quite true, because then things get complicated if you have covariation between regressors and so on. So here the aim is now definitely not to talk about multiple linear regression at length, because what you are interested in, or should be interested in, is GLM analysis of fMRI data. So GLM fMRI, and in the summer term we will talk about the specific forms of multiple linear regression that are interesting for first level fMRI data analysis. Yeah, and they are all multiple linear regression designs. So maybe you've seen that in papers now. Have you heard about this convolution of onsets? Have you seen this? Or that? Yeah, you have seen that. Yeah, so that there's something like the onsets were convolved with the hemodynamic response function. Das ist, glaube ich, besser. Ja. Okay, das lag jetzt nicht daran, dass ich nicht dieses Support-Ding gemacht habe. Ne? Das war einfach so. Spaß. So where were we? Yeah, so that you've seen convolution designs with onset vectors in your papers, yeah, so that you are presenting. So this is first level fMRI data analysis, and we will talk about this in some length in the summer term. So we will not talk much about multiple linear regression now, but we will talk a specific case about of multiple linear regression, namely applying multiple linear regression to the data set that we are currently looking at, because we here, if you go back to the data set, we have two independent variables that you can see as being continuous. So age varying over the participants, and also the alcohol consumption varying over participants. So in this case, this would be a multiple linear regression where you have two predictors or regressors, and would like to then, of course, estimate the effects of these regressors, and then maybe compare whether one of them is larger than the other, so in terms of a t-test. Yeah? And so what I'm doing now is to write down the multiple linear regression for this case of two regressors, yeah, not for the most general setting, just for you to get a feeling of how that looks. So again, starting with the probabilistic version, the idea would be that the ith data point is the realization of a normally distributed or Gaussian distributed random variable with expectation being given by an offset. So this is always what, or this is usually the case that people model an offset in multiple linear regression designs. You will also see that in the fMRI case, where people model the run or session offset. And then, of course, multiple linear regression says that to this offset, you add the effect of the first regressor. So here then, of course, one needs to index the regressor not only for which data point the prediction is made, but also which regressor is actually meant. Yeah? So x1i would be the value of the first independent variable, let's say h in this case, for the ith data point. And then, of course, because we now have two, there's a second one, which would be the alcohol units. And this has then its own slope parameter or effect parameter, B2. So, again, from a structural viewpoint, maybe actually you can tell me what the structural viewpoint is. So what do I write here for the structural view? Basically following just the pattern that we've always done. No, so with the structural, I mean, so with the X beta, this is the GLM view. Maybe I should label them again. So this is the probabilistic view. This is how you find these things in mathematical statistics books, essentially. This is the structural view. This is how you find them in psychological, in statistics for psychologist books. And this I call the GLM view. This is how you find them in my world. So what's the structural view on, if you see this probabilistic view, so that yi is distributed according to this, what's the structural view? Epsilon? Epsilon I, exactly. So this is just interpolation from what we've seen before. It's always the same. It's just a slightly different viewpoint, because this views the whole thing more as a random variable again, and this views the thing as a as the outcome of some addition, but we've also discussed that, of course. In this sense, this is all consolidation, that if you add something random to something deterministic, then you get something random, so it's the same thing. It's just different representations, and you should realize that they are the same, or mean the same thing. Okay, so these are the probabilistic and the structural viewpoint. Now, any guesses on the GLM, how that looks?
Instead of the 2 beta parameters, you have 3, and the design matrix has to have 3 columns.
Yeah. And what are these columns?
I guess the ones again, and the next one.
Exactly. Yep, so. Like this, and then the entries of the beta parameter are
whatever you want to call
yeah.
A, E1, and
yeah. Exactly, yeah. So in principle you can of course call them whatever you want to call them, but so these representations then of course constrain what you can do to them. Then of course, so what I'm for simple multiple linear regression I'm not discussing is that, of course, but you should always have that in the back of your mind when we talk about the designs, that of course you can compute the beta head estimates, or the beta estimates, you can compute the variance estimates, and you can compute t-values based on some contrast. So for example, if you just want to see whether the offset for some reason is different from 0, you could specify a contrast like 1, 0, 0, and then you could use t inference, something you could do. You can of course also, in this case, do an f-test. So what would you need to think about first if you want to do an f-test? Or not an f-test, or computing an f-statistic. So what was the fundamental idea of doing f-statistics? You weren't there, and you haven't watched my YouTube video, because I have all these things on YouTube, so that one can watch them. So does anyone from the f-statistics, does anyone remember what is the first thing that you need to do if you want to compute f-statistics? No? Okay, so that was partitioning the model and doing comparing 2 models. So here you can of course always partition the design matrix either into just a column of ones, or kind of a simple linear regression, and then asking how much additional variance the second regressor explains. So that's something you can do. These things, so I'm not working out all of these details for the designs, because then it would take forever. So in terms of visualization, this is actually something that you will hardly ever find visualized. So economists, they love multiple linear regressions, and they always show you then tables of beta parameters. So they, when you see these tables with beta parameters, psychologists also sometimes do that, but I've seen it more in the economics literature. What is rarely done in multiple linear regression is any attempts on visualization. For the case of 2 regressors, one can actually do that. Yeah, maybe I just tell you how that looks, and maybe then also tell you why you rarely see that. So the thing is, of course, that you now what you want to predict. Maybe let's do it like this. What you want to predict, of course, always in GLMs is a univariate quantity. So you have your DLPFC volume that you want to predict. here on, if you want, the z-axis. And then you have now two predictors, one being age and one being alcohol. Maybe like this. Of course, it's nicer in my script that you have online, and usually also in printed version. And then you're trying to predict that. So for a specific data point, you have a specific value of alcohol. So we call the table. There's of course a specific alcohol unit associated with different participants and a specific age. So you have something in the space of these independent variables that signifies the data point, and then of course it's somewhere, maybe I'll make a large one, it's somewhere in this space is the DLPFC volume. And now if you want to visualize all data points, then of course so you have these 32 values that somehow live in this space. This is quite hard to visualize. Look at it online or look at it here. Now, if one would follow the logic of how this is always visualized in terms of simple linear regression, then of course here you are not predicting a line, but you're predicting a surface, right? Because you have a two-dimensional entity that predicts stuff. So if one fits this, what one gets is actually a surface lying in this space, which I now really have a hard time to draw. Or maybe it works a little bit like maybe a little bit like this. So you have this surface that lies in the space and can be tilted in different ways, right? So if you think about just generalizing from the line that you have in 1D space, then you have a surface that now can tilt in any of the direction. Here it actually, this is what I tried there, but it's not quite easy to see. Here it is tilted down for larger age and larger alcohol levels. So basically implying that the more you drink and the older you get, the smaller your brain gets. It's an artificial example, but this is how one would, one can in principle visualize multiple linear regression. If you think about going to larger designs of multiple linear regression, then of course it really gets hard to visualize things, right? Because then what your prediction, so your expected value, in this case it's a surface, and then if you would now take another regressor in, then your prediction would be kind of a cube, and then you go into higher dimension, you cannot really visualize that anymore. But you should also, in this case of going to multiple linear regression, you can think about things like offsets, right? So that there is some kind of offset that moves this surface in the space of DLPFC, so that the offset usually has kind of a nice intuition. But then, like I said, for some reason these kind of things are never visualized, especially if you have two regressors where one could, and where it's actually not that uninformative to look at that. Yep.
We only have one offset parameter, right?
Yep.
And when I imagine the plane, I could tilt it like that it's on the 0 point on one of its borders, but not on the other. How is that represented in the one? Like A is a combination of for both independent variables telling us, right?
So you want, okay, so let's think about what you actually want. So, so you want a prediction that is just You want a prediction that is essentially this. Okay, so then, so this is your x 1, and this is your x2. And now you want to, of course, only predict values that lie here. So you set the b2 would be 0, and then you're saying, and I can see your point,
like
that
you have no b2, but if you like moved it a little bit like that, you know that it's not vertical, but so you still have some x2 in it. You know what I mean?
Yeah, I mean, I think it's actually harder in this case, but in the case that you're talking about that it's that it essentially looks a little bit like this. Yeah. So then it's essentially like this. So you need, so the way you get to points on the surface is that you go a certain degree independently on this. So this is how you maybe want to look at it. So and there you have to think that it's the average if you estimate the parameters, or also if you predict the parameters, that this offset is kind of the average of everything. And then you go first to the average. So you go here, and then depending on the value of b1 and b2, you go a little bit up, and then maybe a little bit down again. But you have two more values to play with, right? So you know, for this data point, you know the offset, so because that's the same for all data points, and then you go a little bit up, maybe another little bit up. That depends on the values of b1, b2, and the corresponding values of x1 and x2. Yeah. I think what you're hinting at is with this thing that it's completely in one space, that it's not. But that can't be. So no, because then essentially you are in the case of simple linear regression.
Yeah, I think I just get confused what you call it.
Yeah. Cleared up a question. One. There was one question, and that question was cleared up at least. Good. So that's how one can think about these, but there are a lot of problems associated with multiple linear regression, specifically if that essentially relate to this, that you can have different parameter combinations that essentially make the same data predictions, which is always the case if you are levels of the independent variables or your values of the independent variables are also related. So we will come back to multiple linear regression and the problems associated with it for the case that we are interested in, namely first level GLM analysis of FMRI data in the summertime. Yeah. So for now, we have already covered what I want to do in terms of continuous designs. So we can now go to categorical designs. Any questions before we switch? Good. So that was quick. The rest of the stuff will not be that quick. So categorical designs. That's now what we have to work off, and what we want to do is actually to look at the one sample t-test, and we might be able to do that today. And then for the rest, we want to look at the two sample independent because we can only do that in a way. And then we will look at different forms of ANOVA. So we will do one-way ANOVA, and then we will two-way additive, and then we will look at two-way ANOVA with interaction. So this is now really the program for the rest. Not for today, but for everything. And of course there are many more categorical designs that one could look at, but I think yeah, looking at those is what we have the time for, and what you will be also, once we looked at them, be happy with. Good. So one sample t-test. This is again something that we actually seen previously. And this is where also the GLM view, I think, especially now talking about t-test, the GLM view should help you, because previously in undergrad statistics, of course, you saw t-tests, I assume t-tests as something quite different from simple linear regression, right? Or who would agree that you saw t-tests and simple linear regression as different things? Yes, you would all agree. Good. Now we view them as, of course, part of the same story, and we go on basically as previously. So the story about the one sample t-test is that you see the ith data point as the realization of a Gaussian random variable, where you for all variables assume the same expectation and the same variance, again in the probabilistic format. In the structural format, of course, you see this as the same expectation plus the error. And the error is, of course, distributed as always. And then we've seen this also now multiple times in its GLM format, namely that here, if you look at a data set of n data points as a realization of the multivariate Gaussian, maybe I write this again this way, because that's how I write it in the script. So like this. And then it's also not a surprise that the design matrix is what? We've seen this also today. I mean, it's not. Now the only thing that changed was an M von Ö. Yeah, it's a column of ones, and the beta parameter is given as this mu value. So this is the GLM design of a one sample t-test, and we've seen this actually also before. I'm just bringing it up again because yeah, to cover everything that we discuss and to consolidate these things. So remember when we talked about the intuition or the basic intuition of the t-statistic, then we looked at exactly this design, and then looked at what actually falls out for the beta estimates. Do you remember what comes out? What came out there? Maybe look it up. Sure. No, yeah, okay. That's yeah. It's good that you bring that up, because that's kind of the that applies to all of the designs, of course, that we are discussing now. But now the question is, what is the better head estimator in this specific case? Yeah. Yeah, exactly. So in this case, if you have the column of ones, and what we went over there is that then you end up with the sample mean. And for the variance estimate, we also seen this. You end up with the sample variance, which is, of course, as you are familiar with it. So if this is y bar, you end up with a sample variance, and then this is also what we've seen previously. It's discussed again in the script how you get there, but you end up with the formula for the t value, which was the square root of the number of data points, and then the sample mean divided by the sample standard deviation, where S is the square root of the estimate here. Yeah. So remember that we talked about that. Yeah. So we talked about effect size, and we had a discussion about effect size, and told you that the t value gets when you have more data points, the t value at the same ratio here gets larger and larger. So this is just to remind you again that the one sample t-test is readily implemented in the GLM if the GLM takes this specific form. If one wants to visualize a one sample t-test, again, this is something that is rarely being done, but if you think about how, for example, one-way ANOVAs, when you have 3 groups or so, or 2 groups for a 2 sample t-test, how this is visualized, then it follows from that you should, or one can visualize a one sample t-test by a bar, which represents the mean, and some error bar, which, for example, represents the standard deviation. Yeah. And of course, the story about the one sample t-test is then always that you want to contrast the or you want to figure out whether this mu is identical to a given pre-specified value. So your common t-test with the null hypothesis is that mu is 0, and then of course you might observe something like that in the corresponding t statistic, and then say, well, the probability for observing this kind of expectation in relation to this variance, so this t value under this null hypothesis is fairly small, so I reject the null hypothesis, as we discussed when we discussed t statistics. But you can of course also use use the one sample t-test against other null hypotheses, for example, to test it against what people like to do when they do multivariate pattern classification against values of, for example, 0.5, and do a t-test against the probability that this is 1/2 if you have binary classification. That's something more for the summer term in terms of MVPA, and specifically doing this kind of things on the MVPA data is very weird. So it's just some really weird stuff. anyway, it's being done. Good, so that's the GLN implementation of one sample t-test. Questions about this? No, good. So I think this is then where we want to stop for today, because we've basically now rehearsed and then reviewed most of the stuff that we've seen before in terms of designs. So we've seen the one-sample t-test, we've seen simple linear regression. In the very beginning, we also saw multiple linear regression, but that was before we introduced the stochastic part. And I've shown you from the introduction of this whole thing, I've shown you the general scope of where we are. So then next week we can start, or we start with independent two-sample t-test, and then do the generalization to one-way ANOVA directly afterwards, because these kind of go together. Yeah? Everybody happy? Questions? Remarks? Anything? No? Good. Then see you next week or this week, and specifically also this afternoon, because we will have a CCNB seminar. Yeah? Good. Thanks and goodbye.